And now we'll dive into the world of Boolean algebra. This is a form of algebra in which all values are reduced to either true or false. So Boolean algebra is the math we use to analyze digital circuits. These circuits are made up of logic gates. Because all variables are either true or false, it fits nicely with the binary number system, which gives it its use in computer science. For example, when voltage is present, we say that a circuit or a gate is on, or true, closed, high, or assign it a value of 1. When voltage is not present, we say it's off, false, open, low, or assign it a value of 0. Note that some inputs are what we call active low, which means that when voltage is present, the circuit is actually off. There are 3 main logic gates that we need to consider. These alter the inputs to produce a specific output. These are the NOT gate, the AND gate, and the OR gate. When we combine the 3 main gates, we have the negations for AND and OR, not AND or NAND, and not OR or NOR. Another key gate is the exclusive OR, XOR, and its negation, not exclusive OR XNOR. So with these 7 gates, we can create all electronic circuitry. I know there's a ton of information on this slide, but you'll find everything that's here on your formula sheet as well. And what we'll do next is look at each logic gate in detail. We'll look at how it's expressed algebraically, the symbol that's used when we draw our circuits, the action it takes, and therefore what it does with given inputs. In other words, what is the output for a given input? These aren't exactly standard symbol names, so I wouldn't suggest using these outside of the course, but they're just silly enough that they really help me remember. So that's why I've left them on here. We'll use truth tables to determine what all the possible combinations are, what the outputs are for input combinations. Generally, we'll only want to use truth tables if we have 2, maybe 3 inputs, because the number of combinations is a power of 2, where the exponent is the number of inputs we've got. So if we have 3 inputs, we end up having 2 to the power of 3, or 8 possible combinations we have to look at. And you can see that if I have 6 inputs, it gets cumbersome very quickly. To look at all 64 possible combinations would take quite a while. So we'll use these to test simple gates, but we could absolutely use them for complicated circuits as well. So we will see a little bit of this. You can prove Boolean algebra rules and equalities with them as well, and we'll tackle that in the 3rd portion. Let's start 2 very straightforward gates, the NOT gate and the buffer. The only one we'll really end up using here is the NOT gate. So a NOT gate is simply a triangle with a dot in front of it. And here we have input A, and our output we'll write on the other side. The inputs for A can only be 0 or 1. What does a NOT gate do? It gives you the opposite output. It is a negation. So it flips all 0s to 1s and all 1s to 0s. So as I put an input of 0 through the NOT gate, I get a 1 as an output. And if I have an input of 1, my NOT gate gives me an output of 0. The symbol for this, algebraically, is A with a bar over top. So if my input is A, not A, or the negation of A, is A bar. The buffer doesn't do anything, which is why we don't spend a lot of time on it. If I've got an input of 0, it gives me an output of 0. And if I have an input of 1, it gives me an output of 1. What it does is it allows me to store something, or it may amplify your signal. So it's not that it's useless, but drawing it into a circuit, in our case, isn't something that we'll see. All right, so now that we've tackled the NOT gate, we'll tackle the AND gate and the OR gate, as well as their negations, NAND and NOR. And then the last ones we'll look at are the XOR and the XNOR, which are a little bit different. So for inputs A and B, I have 2 to the power of 2, or 4 possibilities. So I'll write half of my options for A as zeros and the other half as 1. And then for the A options of 0, my B's will be half 0 and half 1. And for the option 1, for the input of 1 for A, half of my B's will be 0 and the other half will be 1. It's fairly straightforward to write down all of the possible combinations when I have 2 inputs, but that idea of writing half of them as 0 and half of them as 1 is really useful once we move to 3 inputs and even 4 inputs. All right, so what do the AND gate and the OR gate look like? Got 2 inputs. I'm told they're called A and B, and an AND gate is listed as looking like a plug, and it looks a little bit like a 2-pronged plug. Algebraically, I would write A times B. We can think of AND as multiplication. For an AND gate, both inputs must be true. Otherwise, an AND gate returns an output of 0. So if both A and B are 0, AND returns 0. If only B is 1, but A is still 0, we still get a 0. Same for an input of A of 1, but B and 0. The only way we can get a 1 is if both the A and the B are 1s. We can move right along to NAND before we tackle OR. And the reason is that I'm only going to focus on the AND result, the output of the AND gate, when I write my outputs for NAND. If I want to have a NAND gate, I start with my AND gate. There it is. We'd already drawn it. And we simply put a not dot in front of it. So we have A and B as our inputs, and we're asked to throw them through an AND gate and then provide their negation. The algebraic symbol for that is AB with a bar over both. Okay, all we need to do for the NAND gate is the same as we did for the NOT gate all by itself. We're going to take each symbol, each value input for AND flip it. So all the zeros become 1s, and all, or in this case, the single 1 becomes a 0. It's much, much easier to determine the output of a NAND gate by first determining the output of an AND gate by itself, and then providing the negation. The same is going to be true for the OR and the XOR gates. All right, let's have a look at OR next. What does OR look like? We have 2 inputs called A and B. NOR is just a little bit curvier. It's more or less an OR gate. OR looks like this, A plus B. When we think of AND, we think of products. And when we think of OR, we think of sums. And I'll show you how that works in a moment. Again, the symbol for OR is a plus. The output for OR is positive, is 1, if either A or B, or both A and B, are equal to 1. So if A and B are both 0, that's the only case where OR is 0, and in all other cases, it's a 1. So that's very important, A or B or both. And why do I say that sums are what we're interested in here? Think of it this way. If we take A and B, the inputs, and add them, what do we get? Well, 0 plus 0 is 0. And maybe I'll highlight that for you. 0 plus 0 gives us 0. 0 plus 1 is 1. 1 plus 0, on the other hand, well, still 1. But 1 plus 1, well, it would be 2, but we're in the binary system. Our only options are 0s and 1s, so we simply give it a 1. Say we cap out at 1. Now look at what's happening to give us the AND gate. For AND, we want to think of this as products. So if we take 0 and 0 and multiply them, we get 0. 0 times 1 is likewise 0. 1 times 0, still 0. It's only 1 times 1 that gives us an output of 1. So I'm just providing you with an alternate way of thinking about these gates. While we're looking at the OR gate, and I've drawn one here, you don't really need to draw a separate one, as it is just an OR gate with a not dot. There's my NOR gate, and that's of course going to be A or B negated. So when I write down zeros and ones, the output for the NOR gate, I simply look at the OR and I flip them. So I have 1, 0, 0, 0 for this particular table. Let's clear this and have a look at the XOR gates. All right, XOR for two inputs A and B will look like this, much like the OR gate, but with an extra arc at the back. So for inputs A and B, what are our outputs? XOR is a little bit different from OR because it is the exclusive OR rather than the inclusive OR. In this case, exclusive OR, we've got a true output if A or B, but not both, are 0. So in the case where B is 1, but A is 0, XOR gives me a 1. Where A is 1, but B is 0, XOR gives me a 1. But where both A and B are 1s, I get a 0. So there's the big difference between OR and XOR. The symbol for XOR is a plus with a circle around it. So you'll see this. So we want to think of these as the odd ones. How does that work? Well, if I've got 0 and 0, we know that XOR was 0. 0 plus 1 gives us 1. That's an odd number. 1 plus 0 gives us 1. That's an odd number, so it's true. And 1 plus 1 is 2. That's an even number, so it's 0. One or the other, but not both. And then finally, the XNOR gate. Two inputs, A and B, through an XOR with a negation. There's A and B. We're looking at XOR, or A XOR B with a negation over top. So I'm simply going to take all of the values in the XOR, right? I'm just looking at the column before it and flipping them around. Okay, so we're ready to build a truth table for a more complicated algebraic expression.